Next up, we have Dr. Jakob Lohse from Autodesk. I'm going to add him as a panelist, and he should be appearing on the screen shortly. All right, so Jacob is the senior product manager at Autodesk. His work in integrating machine learning into industrial optimization processes marked his entry into the AI ML field, which has increasingly become his primary focus. Today, he's talking about bringing physics AI into real-world engineering workflows. Hi, Jacob.
Hi, everyone. Thanks for the introduction. Thanks for being here. So we heard lots of interesting presentations, and I want to share some additional presentation material on the interface between engineering and design, especially in the automotive world, and how AI can accelerate those processes. So when we started working on those topics, we always had this vision that people can meet in one room, people from different departments, and they can really work interactively on designing a car. So discuss which are the areas worth fighting for, what areas are absolutely okay, and do everything within the meeting without having to postpone decisions because they lack information. So one way how we could overcome those time-consuming iterative cycles is obviously by using AI models where you can store existing company knowledge. For example, you use existing simulation data and you basically extract valuable information and store it in an AI model. So this is, I would call it, this is one puzzle piece that I want to present because I want to structure my presentation maybe in two steps. First is which puzzle pieces, which functionalities do you need to enable your agents? And then last but not least, what can you do with agentic AI? Right. So first step is use information from existing data and stored in an AI model. So next time someone comes up with a new design, a new shape of a car, a new set of boundary conditions, he can get fast results for engineering or engineering insights in his design work quite fast. So a prediction from an AI model just takes a few seconds, where a simulation would take at least longer than you have time in the meeting. Right. So first approach, this is also a bit of a historical tech wrap up, was when we started 10 years ago, when I started 10 years ago, the world was purely parametric. So you had parametric inputs. So you can change parameter combinations as an input. You get predictions for new geometry. You get predictions for a new flow field. And you also get predictions for key performance indicators like a drag and the lift. So this was our first version of interactive design, but it was very, very manual. So second iteration was that when you introduce deep learning, you can work directly on shapes. So for example, here in Alias, really design a car, and that's quite sophisticated surface modeling. You can work on easier sub-D models. You can work on very sophisticated class A NURBS models. You can do hybrid modeling. But anyways, whenever you're satisfied with the new shape and you want to evaluate the impact of your shape change on the performance of the car, you can simply hit a predict button and you get some information about aerodynamic performance. So at this stage, you know exactly, you have basically two puzzle pieces. You can create a new geometry by either setting a new parameter combination or create a new shape, and you can evaluate the performance. Right. That's what I would call the basics. What's also a basic is that since you always get a prediction, you always need some kind of a confidence measure, like a trustworthiness of the prediction. Can you trust the prediction or not? And if you cannot trust the prediction, you need a clear indication. What is the area that is causing a not trustworthy prediction? I think that's also quite important. And what you also want to know is what we call a sensitivity. So which area is sensitive if you want to reduce the drag of a car or if you want to increase the electronic range of a car. This is something that also comes as a model prediction. And this is something that you can work on with manually. But anyways, you will reach at some time you will reach a point where you say like, yeah, I have an AI model in place. I can do some shape variations. I get instant performance reviews, but I'm not quite pleased with the performance. It's not good enough. It's not fast enough. It's not efficient enough. It's not balanced enough. So what do I want to do? And this is the point where we say, okay, that's the first time where we want to use also AI to generate surfaces. So this is what we call a recommendation system. Basically couples this predictive AI with a generative AI, where you can create basically unlimited new variations, new geometry variations, and then obviously also evaluate the performance of each of those variations. And now you can couple the generative AI model and the predictive AI model with an optimization loop and perform aerodynamic optimizations. This is something that you can do. And the key point here is this is not taking days or weeks. Since you are working against fast AI model predictions, you can do this while you're out for lunch and run an AI optimization. And what happens sometimes in the engineering world is you made up your mind when you return, you look at the results and it's like, yeah, that's okay, but that's not entirely true to all my stakeholders. I might want to change my objective function. I might want to change some constraints. So I need to rerun the optimization again, just with a new purpose. So you can just change this, add objectives, constraints, whatever you want to do. And at the end, it's your choice. You can trust this workflow, this automated workflow that gives you lots of answers, but you can also not trust it and run some simulations, but maybe not on 100 different variants, maybe only on the 5 variants that are most promising. That's number one. Number one, you can also say like, I just take a fraction, some inspiration from it and follow up again. At the end, it's always your choice. So we are now in this presentation at the point where we say like we have different functionalities. Let's call them the API functionalities, where we can create geometries. We can also maybe accelerate the generation of high fidelity, high class surfaces, and then we can evaluate their performance within a quick amount of time. And this enables us to work interactively between different departments or run true optimizations. I think that's quite important, while a human person is always in control. Right. When I talk about different departments, that could also mean that you can apply this technology to different applications, not only external aerodynamics. My background is in external aerodynamics, so I did my PhD working in a wind tunnel, did a lot of CFD method development in the automotive industry, so I like those examples. But you can also apply this, for example, to structural problems like crash or durability, cost of sheet metal stamping, or some other applications. And this also enables you to close this loop or to extend this loop over multiple disciplines. So really have an agent in place that changes the geometry, that evaluates different predictive AI models, that is maybe controllable in terms of what's my actual goal, what's my objective, what constraints do I have, in which shape or form, and gives you some recommendations, which ideas to follow, so that you can really have some confidence to follow your ideas without hesitation. And imagine you're doing a design review and you also want to stream your latest design states into the Apple Vision Pro, for example, using Autodesk Rered combination with the Apple Vision Pro. And then you want to decide on a few changes and evaluate the impact of those changes. See how that impacts not only the shape, but also the aerodynamic performance, structural performance, what's about manufacturing those parts, and also how does it look at the end. And imagine you can orchestrate your agents not only by a prompt, but also by a voice control, have everything inside extended reality, inside an Apple Vision Pro. I think that's a bold future for that. Right. And with that, I want to close my presentation and happy to get some questions.
Wonderful. Thanks, Jacob. It was really neat how you made that analogy where, you can run the AI, run the system, and then go out to lunch, right? You really put that in a practical state, but at the end of the day, you can choose to trust or choose not to trust. And if you choose to trust, then it just reduces the amount of simulations and the variance that you have to run. It doesn't mean that you're taking exactly what is given to you and running with it. It's you still can do other steps and you're in control. I think that's an important point for that trust building that needs to happen with these tools. So we do have a couple questions and a little bit of time. I think this one's for you. What is the approximate ratio between compute demanded for training versus compute spared due to DL prediction of CFD fields or geometries?
Right. I think this technology, especially if you start working on this technology, is not about saving computational efforts. It's about left shifting simulation. So you create knowledge and you store that knowledge in an AI model. And instead of opening 200 high fidelity CFD simulations, which are roughly 60 gigabytes each, you can access an AI model within seconds. I think that makes a large difference and enables lots of possibilities where you can really see interactions between different feature changes that you might not see if you need to open one case by another.
That makes a lot of sense. Another question for you. I noticed the fluid option in the generative design extension of Autodesk Fusion is no longer available. Will this come back in another module or product? You have any intel there?
Right. So we are working in the ACX compartment, so it's automotive design. So our software is really used. Our software is like Alias and Fred, which is used in a design studio. Um, it's a bit different. So Alias is more as a surfacing tool, while Fusion is really a CAD platform. So
Hopefully that answers that. I have a question to add on to actually, kind of tying in some of the previous presentations that we've heard with organizational change. Is this requiring new skills for engineers, especially if you're talking about, left shifting? Is this adding more to the workload? With design for manufacturability, cost basis analysis, all that stuff. Even Mark presented how AI can do a lot of those calculations up front, so that left shift isn't adding more and more workload to design engineers. It's actually allowing that left shift to happen more efficiently. Can you comment on that?
yes, I think it adds not more mental load. So at the end, you need to produce those data sets, but you can also benefit from older data sets. And I think what really accelerates those design and engineering processes is that if you have the AI model in place, you can really work more interactively. So you break this iterative cycle where you say like, I cannot make a decision. I need to wait for some new results. And then the engineering team is under a lot of pressure to deliver those results, have meaningful results. And while you are waiting for those results, the world does not stop. So we heard about those goals, faster time to market. There is like the competition from the Far East, which is much more, yeah, which is faster in terms of developing products. So this is I think it's really a change, and it's supposed to make things easier because you don't need to know specifically what you need to work on. You can set a design space, and at the end you know a bit what are the boundaries of my product development. So you can capture those design spaces and make all those specific decisions. What are constraints? What are constraints from department A or B? You can do that later in the process.
Very good. Thank you, Jacob. Again, any more questions for Jacob, feel free to continue them in the chat. He also provided his contact information. Really appreciate that presentation.
You're welcome. Thank you for having us.
And we'll see you shortly as well in the panel discussion, so don't go too far.
Yes.